So let's now take a look at how we would analyze a problem and just look at the life cycle of a program. So before we just start typing away and hacking code, we need to understand exactly what programming is. It's not just typing away, hacking code, and see what you come up with. No, it doesn't work that way. Programming is a process of problem solving. That's the whole purpose of programs. It's to solve problems. In fact, computer science itself is simply the study of problem solving. And we're coming up with different tools and different approaches for solving these problems and making them easier for us. So it's our job as programmers to come up with the steps for solving a particular problem. Writing code and running it on a computer is a way to actually solve the problem, but we're still coming up with those steps. So if you want to be a really good programmer, you need to have some good problem solving techniques, and we'll be going over several of those techniques in this class. One such technique, and this is a very common technique, involves analyzing the problem, outlining the requirements for solving that problem, and then designing the steps of that problem. And this design, these set of steps, is what we call the algorithm for solving a problem. In fact, it's a really good idea to get in the habit of writing up the list of steps, writing up your algorithm before you start typing away on code. Think of an algorithm as kind of like the blueprints of it. I mean, let's say you're going to be building a house. You don't just start putting a couple 2x4s together, put some nails and hammer them together, and hope to build your house. I don't think anyone has been able to pull that off. You need to come up with a plan first. You have your blueprints, you come up with your foundation, and then you set up the rest of the house and put in all the features. The same thing is true for programming. Before you just start typing code, you need to come up with a plan ahead of time for solving your problem and writing your code. So it's good to get in a habit of that. Now, the problem solving process itself has 5 different steps. The first step is to analyze the problem. So we need to outline the problem and come up with the requirements for the solution. You may think this is not a big deal, but this is actually the most important step in the process. I mean, think about it. If you're going to solve a problem, you need to know what the problem is before you try coming up with a solution. Otherwise, you could be coming up with a program that solves a completely different problem, or maybe it only partially solves your problem. So we need to make sure we understand the problem in order to come up with our solution. So the way we analyze it, we need to do the following. We first need to thoroughly understand the problem. We need to know the ins and outs of it. We need to know exactly what it is that we're trying to solve. And then we need to understand the problem requirements themselves. Now, what do we mean by the requirements? Well, we need to ask ourselves some questions like, does this problem require user interaction? Do we need to make changes to data? Do we have to produce output for this program? You might think that all programs use all this stuff, so we just assume that we need these steps, but some programs don't work that way. So we need to make sure we know exactly what is expected out of our solution. And let's say the problem is really complex. Trying to just solve the whole thing from start to finish is going to be quite tedious. So instead, we may need to actually divide the problem into smaller problems. And each of those smaller problems would be a lot easier to solve. So we'll be looking at some techniques later on helping us with dividing a large complex problem into a bunch of smaller, more manageable subproblems. The next step is to design your algorithm. And we've kind of already mentioned before about it, but the idea with this is for every problem and subproblem that we have, we need to design an algorithm or the list of steps to solve it. So as I've said earlier, think of this as the blueprints of your program. We need to come up with your plan before you actually start coding. And the reason why I really emphasize this is because a lot of programmers just think that the algorithm is not important at all, that they can just take a look at the problem, they understand it, and they can just skip this step and start coming up with a solution. But it's actually going to save you time to come up with the algorithm first. A lot of people think that writing an algorithm is a time waster because you're spending time writing something on a piece of paper or typing up steps when you should be working on code. But if you take a decent amount of time for coming up with your plan, when writing the code, it's actually going to go by a lot quicker than if you try to write a program without an algorithm. The third step is to implement the program. So I mean, once you have your algorithm, you can start typing code. So you're going to want to use an appropriate programming language. So in this class, we're going to be talking about Java, but depending on the type of problem, it might be more appropriate to use a different programming language. You're going to need to use some text editor if you want to create the source code. So we went over several examples. So normal text editor, Dr. Java, Eclipse, whatever you're comfortable with is perfectly fine. Now in this class, I will be using Dr. Java to demonstrate a lot of our code, as you've already seen at least one example of, but you're welcome to use any text editor that you want for your programs. And then once you've written your programs, then you're going to need to use some compiler to make sure that the syntax is correct. And you might think, well, I mean, you've got to compile it, but I'm sure everything will be just fine. I'm going to say right now, it's very, very rare to write a lengthy, complex program without having any compiler errors on the first try. I mean, I've been doing coding for many, many, many years, and even I still get compile errors when I write programs. So if I get compile errors when I write programs, you're going to get compile errors. So it's just part of the process. It's going to happen. Now, once your program is written up and it's compiled, we can then move on to the fourth step, which is to test your program. So we need to run it in order to make sure it actually works. You can't just type it up, compile, and then just let it go and think that it's going to work. You need to run it to make sure everything is working properly. Because just because a program is compiling correctly doesn't mean your program is actually correct. There could be problems that happen while running the program. Maybe you put a line of code that does something than what you thought it would, so you get a different type of output. Or even to make matters worse, you could have a runtime error that causes your program to terminate abnormally or even crash. So you got to make sure that everything there is working properly before you can say that your solution is done. And then the last step is to update and modify your program. Now, for this class, when you type up and write your solution to a program, you're pretty much done with it after everything is working. But in reality, programs do change over time. There could be some new features that need to be added, and also programs need to be able to work on new operating systems. So like, just to give you an example, let's say you write an app for an iPhone, and then the next version of iOS comes out. I mean, it's possible that your app will work on the new iOS without any issues, but most likely there are going to be some new features that you have to make sure that your version of your app does work for the new version. So you may have to make some changes to your app and then put a new version on the store for everyone to download. So you got to make sure it is working based on the new environment. And also there could be some new bugs. You may write a program and it works just fine, and then maybe 6 months down the road you run your program again and you discover a new bug that just wasn't there before, or you never had that particular test case to trigger that bug. So you need to make sure that you handle those new bugs and then send out the updated version. In fact, it's usually very rare for a program to be completely ignored after you complete the original version. There's always going to be new features that you need to have. So maybe you're writing a program for a company, and then that company upgrades their system, so you'll need to update your program to work on the new system. Or maybe your client has a new feature that they want added a year from when your original program was made. So you need to be able to add that new feature into it. So I mean, the point is, programs are going to change over time. Now, as I said before, the first step, the analysis part of it, that is far more important than the program itself. It's more important to make sure you understand the problem, and then you're designing an algorithm for your solution before you start hacking away code. You do not want to start writing code as your very first step. That is the worst thing you can do. You may think that you're trying to save some time by just start writing code because you think you know how to solve the problem, but it's going to come back and bite you later on if you're not careful. If you come up with a well-analyzed and designed algorithm, it's going to be a lot easier to discover errors in your program. If you just start hacking code right away and then you discover an error, you might be spending a lot of time trying to figure out what actually caused it. But if you wrote an algorithm beforehand, you can just compare your code with your algorithm to make sure that you are following the steps properly. And also, this makes writing your code easier to follow and modify if you come up with a plan ahead of time.
Let's take a look at an example where we are trying to compute the perimeter and the area of a rectangle. And in this case, we're only going to worry about the first two steps of the process, analyzing the problem and designing an algorithm. So let's first focus on the analysis portion of this problem. The first thing we need to ask ourselves is, what is it that we're trying to solve? We need to make sure we understand what the problem is asking from us. In this case, we're just trying to compute the perimeter and the area of a rectangle. It's pretty straightforward. So we know what the problem is. So now we need to make sure we understand the problem requirements. So we have to ask ourselves, what information do we need in order to solve this problem? Well, if we're going to compute the perimeter and the area, we should know some information about the rectangle. It means we need to know the length and the width. Now, is this enough information? And the answer to that is no. This is not enough in order to compute the perimeter and the area. I mean, we need to know what the formulas are for computing the perimeter and the area. So we need that information. Well, the formula for the perimeter is just 2 times the length plus width, or you can just say 2 times the length plus 2 times width. Either one is fine. And then to compute the area of a rectangle, you would take the length and multiply it by the width. This should be all the information we need. We need to know the length and the width of the rectangle, and we need to know how to compute the perimeter and the area. So we've taken care of the analysis portion. So now we can move on to creating our algorithm. So the normal way that you would write an algorithm, you can kind of think of it as 3 parts. You would get your inputs, you would do your calculation, and then you would do some type of output. In this example, we're just going to worry about the computation. We're not going to display the output, but we normally would do that. So the first 2 steps would involve getting our input. So we need to get the length, and we would need to get the width. Once we have the length and the width, we can do our computations. So the next step would be to compute the perimeter, which we've already determined that it's 2 times the length plus the width, or the quantity of the length plus width, I should say. But we get that information, and then our last step would be to compute the area, which is simply the length times the width. So once we've completed this algorithm, I mean, we could move on to the next step and implement it, run it, test it, and debug it, but this algorithm would give us the perimeter and the area of a rectangle.
Now, you may have noticed in the algorithm, particularly in steps 3 and 4, we didn't write complete English sentences. We also didn't write any code either. Instead, we kind of did a combination of it. We wrote what's called pseudocode. Now, pseudo means fake, and it kind of sort of means we wrote fake code. The idea with this is that we can write an outline of our program, and we can take this outline and translate it into the actual code itself. So pseudocode is not written in any particular language. We can use it for any program we want to do, for any language we want. It doesn't matter what language, but pseudocode is high-level language independent. It also doesn't have any syntax rules. So like, for example, in most high-level languages, you would end a statement with a semicolon. You don't have to do that with pseudocode. You don't have to end it with any punctuation. The whole purpose of pseudocode is just to show the programming steps. So one way I would suggest going about it is, if you were to verbally explain your algorithm to someone, what you say would be similar to pseudocode. It's just now you're writing it down.